Hope your week is going good. This is another video for you for your Wednesday lecture. And we left off talking about relative dating and how we use it. So let's continue on with that for a moment. Let's do this together. We're going to do this is straight out of your textbook. We're going to do relative dating for the Grand Canyon. Let's see if you can do this. And I know you can. This is from your textbook. Grand Canyon is one of the best places in the world to see the history of the Earth. More geologic time is recorded there than anywhere else on planet Earth. Let's first take a look at this diagram real close. Here you have Vishnu basement rocks, and these are the rocks on the very bottom of the Grand Canyon. These are the oldest rocks in the Grand Canyon. Here you can see this pattern here. That's metamorphic rock. Then you can see this igneous rock with a stippled pattern. And these igneous dikes are cutting through the metamorphic rock. So what's older, the metamorphic rock or the igneous rock? Well, we know from the principal cross-cutting relationships that the Vishnu schist must be older than the granite because the granite cuts through the Vishnu schist, according to the principal cross-cutting relationships. The blue rocks you see here are all formed by, they're all sedimentary rocks, so they're all formed by sedimentation. Here you have these red rocks here, which are tilted at an angle, they're dipping, and they're beneath these blue sedimentary rocks. So which is older, the Grand Canyon supergroup rocks or the layered Paleozoic rocks? The Grand Canyon supergroup rocks must be older because they are underneath the layered Paleozoic rocks. Another way of saying it is, this rock up here, which happens to be called the Kaibab limestone, is the youngest rock found in the Grand Canyon. The Kaibab limestone up here is 250 million years old. That's what happened to the rocks that formed over the last 250 million years. They've been eroded away. Okay, now let's look at these wavy lines. Here's an unconformity here, one here, one here, and one here. What are these? What type of unconformity is this? First, this one right here. And what kind is this one right here? And what kind is this one? And what kind is this one? Well, this one right here, you got metamorphic rocks underneath sedimentary rocks. So this must be a non-conformity. This one right over here has sedimentary rocks beneath the wavy line, and they're dipping at a different angle than those above. What type of unconformity is this? Let's imagine that you're taking a test right now. Is this A, disconformity, B, angular unconformity, or C, a nonconformity? You need to know this. It is a angular unconformity. So this one's a nonconformity here, and that's an angular unconformity here. You got another one right here. Here you have sedimentary rocks, which are called the Tonto group, and they're dipping in the same direction as the sedimentary rocks above. So what type of unconformity is this one right here? It's a disconformity. How about this one right here, where you have sedimentary rocks above and below, and they're dipping in the same direction? What's that one? It's a disconformity. Okay. Now the last thing you need to know here, well, actually, let's just go this far now. Later on, we'll go further. Let's do the geological history of the Grand Canyon. What happened first? Well, we say first thing that must happen was the Vishnu schist formed. We can't say the Vishnu schist was deposited because only sedimentary rocks are deposited, right? So the Vishnu schist formed. Then what happened? Then igneous dikes intruded into the Vishnu schist. Then what happened? Well, then we got our unconformity. So then we have uplift and erosion forms a, what type of unconformity? A nonconformity. Then what happens? Then the Grand Canyon supergroup was deposited, right? Then what happened? Well, Grand Canyon supergroup was not originally deposited at tilted or dipping. Instead, it was originally deposited horizontal. So what must have happened next is the Grand Canyon supergroup was tilted by an earthquake. Then what happens? Another unconformity. So then uplift and erosion forms a what? Angular unconformity. Then what happens? Then the Tonto group, which is sedimentary, was deposited. Then what happens? Then uplift and erosion forms a disconformity. Okay? Then what happens? Then this limestone was deposited. Limestone deposited, bed deposited. Then what happened? Uplift and erosion forms a disconformity. Then what happened? Then layered beds 1 through 5 are deposited. That's these 5 beds. This is the correct history of the Grand Canyon using the principles of relative dating. This shows you how long ago they occurred. Each of these rocks formed in millions of years, and this shows you how thick each layer is. If you ever get to go to the Grand Canyon, it's just, there's no place on earth like it. People in all 50 states and all 13 Canadian provinces, all around the world, go to the Grand Canyon to see the geology there. So that's your answer there. See if you can put this away and then get that same answer. If you could do that, you're in good shape. Let's do one more relative dating exercise before we get into absolute dating. Let's do this is out of your textbook. Let's do the relative dating for this. Okay, now it says here A is metamorphic gneiss. That's A is all of this folded rock. B is an igneous granite, so it's a plutonic rock. D here is an igneous dike, it's a basalt. And C and E are the sedimentary layers on top of this metamorphic gneiss. Okay, let's do the historical geology here. What happened first? Metamorphic gneiss formed. It's on the bottom. Then what happened? Well, let's look at this real careful here. What happened next? Well, you got four things here. You got a fault here, a fault here, and a dike here. Notice that this fault here stops when it comes into contact with this dike. In other words, with not this dike, with this batholith. So this igneous pluton cuts through this fault. Therefore, fault C cuts through gneiss, right? Then what happens? Igneous pluton B cuts. This fault is fault A. I'm sorry. Fault A cuts through gneiss. Igneous pluton B cuts through fault A. Then what happens? Well, then we have this wavy line. So we have a what happens? Uplift. Always when you see that wavy line, it's always uplift and erosion. Forms a what type of unconformity? Okay, this might look like an angular unconformity here, but it's not because it's metamorphic beneath. So it forms a nonconformity. Then what happens? Well, what must have happened next is beds C and E are deposited. Because they're on top of all of the unconformity. Then what happens? Then dike D cuts through bed C. What happens at the very end is this fault cuts through pluton B, gneiss, and beds C and E. Okay, there's the answer for that one. So we're going to practice this next week. You're going to do this. Always start with the first thing on the bottom. Not on the top. And try and work your way up. Okay, that's relative dating. Next thing we're going to talk about is absolute dating. But now it's time for a 1-minute commercial break for the sponsor. So let's watch that here. This is your 1-minute commercial.
You know, if you were to follow a busy doctor as he makes his daily round of calls, you'd find yourself having a mighty busy time keeping up with him. Time out for many men of medicine usually means just long enough to enjoy a cigarette. And because they know what a pleasure it is to smoke a mild, good-tasting cigarette, they're particular about the brand they choose. In a repeated national survey, doctors in all branches of medicine, doctors in all parts of the country were asked, "What cigarette do you smoke, doctor?" Once again, the brand named most was Camel. Yes, according to this repeated nationwide survey, more doctors smoke Camels than any other cigarette. Why not change to Camels for the next 30 days and see what a difference it makes in your smoking enjoyment? See how Camels agree with your throat. See how mild and good-tasting a cigarette can be.
Okay. That's your commercial. I don't know how to get out of this. Okay. That's your commercial there. All right, absolute dating. Absolute dating is figuring out how old the rocks are, and that's getting a number. Now, that wasn't possible until Madame Marie Curie discovered radioactivity in 1900. So don't forget, Madame Marie Curie. And her husband helped Monsieur Pierre Curie. He ran a lot of the experiments. Now, how does radioactivity work? Radioactivity means that you need to understand what this word means. Isotope. What is an isotope? Okay, so let's figure that out first. What is an isotope? Okay, carbon is a common element, and on your periodic table, it's represented by the capital letter C. Let's go look at our periodic table again. And we studied that earlier on, but let's take a look at it again. Periodic table. All right, now you could print one of these out for yourself. You don't need me to do it. I hate this crap. Let's see if I can get one that will just show it without me clicking on a million different things. Okay, C here. I wonder if there's a way of blowing that up. There's carbon right there. Okay, now print out a periodic table, and you can see that. I know you can't see it very well here, but carbon has an atomic number of 6, and it has an atomic mass of 12. Okay? You remember how we did this before? And print out your own one, because I don't want to waste your time by looking for a periodic table, but print out your own, and you'll see 12 on the 12 point something or other here on the bottom, and 6 right here. 6 is the atomic number of carbon. 7 is the atomic number of nitrogen. 8 is the atomic number of oxygen. On the bottom, you have the atomic mass, which we round to the nearest whole number when we're using the Bohr model. So you got 12 here and 6 here. How many protons are in a carbon atom? Do you remember? 6. Because the atomic number is equal to the number of protons in the atom. How many neutrons do you have in a carbon atom? Remember how to do that? Take the atomic mass and subtract the atomic number, and you get the number of neutrons in the atom. So the number of neutrons in the carbon atom should be 6, right? Let's do one more here. Uranium has an atomic number of 92. How many protons are in the uranium atom? 92. It has an atomic mass of 238. How many neutrons are in a uranium atom? Easy. 238, which is the atomic mass, minus the atomic number gives us the number of neutrons, which is 146. Right? So that's how you figure out protons and neutrons for an ordinary, for most atoms. However, look here. There are 3 types of carbon. Carbon 12, which is the most common, but we also have another type called carbon 13 and another type called carbon 14. But instead of saying types, we'll say we have 3 different isotopes of carbon. Carbon 12, carbon 13, and carbon 14. Carbon 12 has 6 protons in it, so does carbon 13 and carbon 14. The difference is the number of neutrons. How many neutrons are in this isotope of carbon, carbon 12? 12 minus 6 is 6. So there are 6 neutrons in carbon 12. How many neutrons in carbon 13? 13 minus 6 is 7. So there's 7 neutrons in carbon 13. How many are in carbon 14? Atomic mass is 14. atomic number 6, so there are 8 neutrons in carbon-14. See, and that's what this is trying to show you in this diagram, is that the purple spheres, that means there's more neutrons. Another way of saying, so there are 3 isotopes of carbon, carbon-12, carbon-13, and carbon-14. Carbon-14 is the heaviest isotope because it has more spheres in it. Carbon-12 is the lightest isotope of carbon. Now, the next thing you want to know is that some isotopes are unstable and some are stable. So an isotope is either stable or unstable. But instead of using the word unstable, chemists use the word radioactive. What's the difference between a stable isotope and a radioactive isotope? Well, a stable isotope is an isotope that is stable. It doesn't want to change into anything else. It stays the same. So a good example of a stable isotope would be, I don't know if there's, let me see, let's see, lead-208. Lead-208 is a stable isotope. So lead-208 stays the same. It doesn't change. Imagine this. Let's say I gave you a cube 1 inch by 1 inch by 1 inch of lead 208. And let's say it weighed 15 ounces. And I put it right there on your desk in front of you, or your sofa, or wherever you're sitting right now. Now let's imagine we move forwards in time 1,000,000 years. How much is that cube going to weigh 1,000,000 years from now? Exactly 15 ounces. It's not going to change. It's going to stay the same. On the other hand, some isotopes, such as carbon-14, are radioactive, meaning that they're not going to stay the same. One type of radioactive isotope is one that undergoes something called alpha decay. Alpha decay, ALPHA. Okay, let me see if I can get a nice picture for you. Oh, this is a real good one here. Okay. Here's radium, Ra. On your periodic table, you'll note that it has an atomic number of 88, and it has an atomic mass of 226. So there's 88 protons in a radium atom, and there's 138 neutrons. 226 minus 88 is 138, right? Radium-226 is radioactive. It does not, it's unstable. It has to change. It changes into this, radon-222. And it releases this particle here called an alpha particle. An alpha particle has 2 protons in it and 2 neutrons. So, radon-222, we call it the daughter product, the daughter of radium-226. Radium-226 since it changes into radon-222, is called the parent of radon-222. So radium-226 is the parent of radon-222. Radon-222 is the daughter of radium-226. Think about it like this: if you're female, um, you came from your parent. Well, radon-222 came from its parent, radium-226. And if you're a parent, you can think of it like this: radium-226 made its daughter, radon-222. So, since this is alpha decay, you can't lose protons and neutrons, and so matter cannot be created or destroyed. So the difference between radon-222 and radium-226 is radon-222 has 2 less protons in it and 2 less neutrons, and that accounts for this. So look at it. It's not complicated, ladies and gentlemen. People get intimidated by this chemistry, but look at what's really going on. It's not that hard. 222 plus 4 is 226. 86 plus 2 is 88, right? So, with every alpha decay, the atomic mass of the daughter goes down by how much? 4. And the atomic number of the daughter goes down by 2. So with every alpha decay simply is the result of the unstable nature of radium, so that it loses 2 protons and 2 neutrons. And these 2 protons and 2 neutrons that are lost are called an alpha particle. Okay? Now, let me ask you a question. If you can answer this question, you know how alpha decay works. Radon-222 itself is radioactive. It's also radioactive. Who is its daughter going to be? Well, that's not hard to answer if you think about it, because radon-222 also undergoes alpha decay. So its daughter is going to have 2 less protons in it and 4 less neutrons. Two less protons and 2 less neutrons in it. So it's going to have an atomic number of -2 and an atomic mass of -4, right? So the atomic mass of the daughter of radon-222 will be 218. 222 minus 4 is 218. And the atomic number will be 86 minus 2, which is what? 84. So then you just go to your periodic table. And lo and behold, the daughter is going to be who? Polonium. Because the polonium is element number 84. It has an atomic number of 84. So with each alpha decay, the atomic mass goes down by 4 and the atomic number goes down by 2. These are all alpha decays. The daughter of polonium-218 is going to have an atomic number of 84 minus 2, which is 82. Looking at your periodic table, that would be lead, Pb. And it will have an atomic mass of 214. Alpha decay is the result of the release of 2 protons and 2 neutrons from the nucleus of the radioactive parent. That's called an alpha particle. Uranium-238, we studied in Oak Ridge a lot, has an atomic number of 92 and an atomic mass of 238. It releases 2 protons and 2 neutrons, otherwise known as an alpha particle, and it makes its daughter, thorium-234. There it is, alpha decay. the release of 2 protons and 2 neutrons, changing the parent to its daughter, so that the daughter has an atomic number of -2 and an atomic mass of -4. There's your periodic table right there. So you can practice this by looking at the periodic table. Now let's talk about beta decay. So there's 2 main types of radioactive decay. There's more than 2, but in this class we're just going to cover the most 2 common ones for natural radioactivity. The second one is called beta decay. Beta is the second letter in the Greek alphabet. What's the difference between beta decay and alpha decay? Well, let's take a look. Let's do carbon-14. Carbon-14 does beta decay. Carbon-14 is unstable. Carbon, if you look at your periodic table, has an atomic number of 6. Look at your periodic table. It has an atomic number 6. It makes a daughter, nitrogen, capital N. Look at your periodic table. It has an atomic number of 7. Carbon-14 is radioactive and it changes into its daughter, nitrogen-14. Carbon-14 and nitrogen-14 have the same atomic mass of 14. The difference is that carbon-14 only has 6 protons in the nucleus of its atom because a carbon has an atomic number of 6. Nitrogen-14, number 7 on your periodic table, has 7 protons in the nucleus of its atom. The way carbon-14 decays or changes into nitrogen-14 is through the release of a particle called a beta particle. So carbon-14 releases a beta particle from the nucleus of its atom. And there's a cockroach here, and I'm going to kill it, so I'll be back.